Alright guys, this is Stats 5.4, and we're going to be kind of talking about geometric and Poisson distributions today. So, first off, we're going to talk about geometric distributions. So, this is the probability of you having your first success on the nth number of trials. So, let's say I want to roll a 6-sided die and say what's the probability that I roll my first 3 on my 5th roll, right? That I can answer that type of question. Now, typically, you're going to use this for things more than that. So, like, hey, what's the probability that it takes me at least 3 rolls to roll a 3, or that I'll roll a 3 on my first 6 rolls, stuff like that. But this is the kind of base part of it, right? So, how we find that probability, right? So the probability that it happens on the nth trial is the probability of success times 1 minus the probability of success, which is also known as my probability of failure, or like Q, right, raised to n minus 1. So, and that should make sense because I have to fail this many times, which is n minus 1. So if I want 10 trials, I have to fail 9 times and be successful once. That's effectively what that means. And then our mu, which is going to be our expected value here, is just 1 over p, right? Which seems a bit weird, but if you think about, hey, your probability of like a coin flip, right? Your probability of a heads is 1/2, right? So what's my expected value of flips that I would need to flip to get a heads? Well, 1 over 1/2 dividing by half is multiplying by the reciprocal. So then I get 2. So you would expect 2 flips before you get your first heads, right? Could you get your first heads on your first flip? Sure. Could you get it on your 8th flip? Sure. So, but the expected or the average number that it would take you is 2, and that's effectively what that's saying there. And then for our standard deviation, again, I'm not going to show you where that comes from because it's quite complex, but it's just the square root of 1 minus p over p. All right, so let's go over this example here, right? So let's assume that you have an 80% chance of being successful in completing a problem, and you want to keep trying until you are successful. So what's the probability that you will be successful on your first, second, or third try? Well, for my first try, right, for n being 1, right, that would be 0.8, because that's my probability of success, times 1 minus 0.8, or 0.2, because that's my probability of a failure, raised to the 1 minus 1, which is 0, because I don't fail here. I just get it right, I'm done. So it's just going to be 0.8 for my probability of getting it right on my first go. You could probably figure that out without the equation, but just for the sake of being complete here. So what about my second try, right? So my probability of being right on my second try is going to be 0.8 times 0.2 raised to the 1, because I need 1 failure and 1 success. And then probability of being right on my third try would be 0.8 times 0.2 raised to the second power, because I need 2 failures and then my 1 success. So if I add all of those up, 0.8 plus 0.16 plus 0.032, which is what you get if you multiply all of those out, you get 0.992, saying that, hey, there's a 99.2% chance that you're going to get it right within your first 3 tries. And a very good chance that you'll get it on your first try, in fact. So that's kind of how we kind of use these. So you can hopefully see where this kind of distribution would be a useful thing for us to have. All right, next one we have here is what's called a Poisson distribution. Now, if you speak a little bit of French, you might know that the word poisson is French for fish. Why it is called a fish distribution then is because this was created by a French statistician who was studying how many fish were being caught in lakes, right? And so he developed this distribution to help answer those questions. So it became known as the Poisson distribution. Okay, so how we use these are for if we know what we would expect on an average period, right? And then what's the probability of getting this other number on that same period, right? So we're going to introduce our first new variable here. This is the lowercase lambda, right? And lambda is the average number of successes, or the mean number of successes, or the expected value. Okay, it's those kinds of things, right? And then R is the actual number of successes, right? So our equation is the probability that I have R number of successes is E raised to the negative lambda power times lambda raised to the number of successes power divided by the number of successes factorial. That's a bit of a mess, right? But it just all comes down to plugging it into your calculator, right? I'm not going to go through the derivation. You see that there's an E there. Whenever you see the number E, that means you effectively have a limit that is happening here, which means we're doing calculus in order to derive this. So it's messy and it's ugly, but it works. You're going to have to trust me on that one. The big benefit here is this is by far the easiest equation for a standard deviation. You're going to see it's just going to be the square root of that lambda. All right, so in the spirit of the history of the Poisson distribution, our first example here is about catching fish, right? So let's assume that we catch an average of 3.5 fish in a 4-hour period when fishing on this lake, right? So that is the average number of fish you would catch, or the number of fish you would expect to catch in a 4-hour period, right? So what's the probability that you would catch at least 3 fish in a 4-hour period? Okay, so I could catch 3, 4, 5, 6, 7, 8, 9, 10, up to a million, right? Or effectively up to infinity, right? So what I could do is I could say, well, I'll plug in my P of 3, right? So I do E raised to the negative 3.5 power times 3.5 raised to the 3 all over 3 factorial. And there's my probability of catching 3 fish, right? But then I gotta find out my probability of catching four fish. So I do the same thing, but plug in a 4 for my R's. But then I gotta do 5 and 6 and 7 and 8 and 9 and 10, and you start to see the problem. I gotta keep doing this again and again and again for every number up into infinity, which I don't want to be doing because I want to do other things before I die, right? So how we can do this is with a converse. We kind of mentioned in chapter 4, these converses are important for us because they allow us to kind of look at, well, let's look at when it doesn't happen and just do 1 minus that, and then we got it. So if I find my probability of getting 0, 1, or 2 fish, that's all of the chances of me not being successful here and catching less than 3 fish. So just do 1 minus that. So that's what I'm going to do, right? So we're going to do E raised to the negative 3.5 power times 3.5 raised to the 0 power over 0 factorial. Do that, then do the same thing for R is 1, do the same thing for R is 2. Get those 3 numbers, pause, get them, and then come back here. All right, so you should get, for those 3, and then we add them all up, we get 0.3209, right? So that's my probability of catching 0, 1, or 2 fish in this 4-hour period. Now since I want 3 or more, 3 or more is every case other than 0, 1, or 2. So I just do 1 minus that 0.3209, and I get about 67.9% chance of catching 3 or more fish in this 4-hour period. And that's, again, effectively where this Poisson distribution came from, was this kind of trying to find the average number of fish being caught in a lake. So there's another use for Poisson distributions here, right? And that is for extremely rare cases. So the binomial distributions we went over in 5.3 work great, except when things are super rare, right? If I'm trying to find the probability of a super rare thing happening, like some person having some rare genetic disorder, right? That binomial distribution is not going to work because it's such a rare thing that I'm not going to ever get that pretty bell curve out of it, because I'm in like 1 out of 1,000 cases. And so if I have a sample size of 200 people, odds are I'm not going to have anyone who meets that criteria. So it just really doesn't work. So a Poisson distribution is actually quite good at making approximations with those super rare cases. So that's what we're going to look at here. So how we define a rare case is if your value of n, so your sample size is greater than 100, and your lambda, or your expected value, is less than 10 at the same time. So anything that is less than 10% chance of success with greater than 100 sample size, right? And the more rare it is, the better it is, right? So it's usable at a sample size of 100 and a lambda of 10. But it's even better when your n is 1,000 and your lambda is 2, right? It gets better and better and better the more rare that ends up being. Okay, so variable-wise here, it's all the same stuff we had earlier. N is our samples, our number of trials, or our sample size. R is our number of successes. P is our probability of success. And then lambda is our expected value, which is just the number of trials times the probability of success. So again, it's that same mu we've been looking at in the past, but we use lambda for Poissons. So then we have our probability of our number of successes. That's the exact same equation you just got in the last slide. So don't feel like you gotta take that down another time. So let's try it out. So we have a rare gene that only occurs in 3% of the population, right? So if I have a group of 180 people, I want to see, and I want to randomly test them for this gene, what's the probability that 3, 4, 5, 6, or 7 of them have the gene? So is this worthy, right? Well, my sample size is larger than 100, so that's good there. My lambda is going to be my sample size times my probability of success. So if I do 180 times 0.03, I get 5.4 for my lambda. So my lambda is less than 10 by a good amount here. My n is greater than 100 by a decent amount. This is a prime candidate for a Poisson distribution, because again, that's a fairly rare case for me, right? I'm going to expect 5 people till I get it, right? So if I hop back over here, let's go ahead and try this out. So what I want you to do, pause, plug in, so we have e raised to the negative 5.4 was the lambda we found, times 5.4 raised to the 3 over 3 factorial. Then do that same thing for 4, for 5, for 6, and for 7. Let's see what you get. All right, so now that we've done that, oops, button. There we go. So we should get 0.1185 for 3, 0.1600 for 4, 0.1728 for 5, 0.1555 for 6, and 0.1200 for 7. So again, we should kind of notice that peak around 5, which makes sense, right? Our lambda is what our expected value is, and ours was 5.4. So we should see that peak be in the kind of 5-ish range, right? And that's kind of what that Poisson distribution is. And if we graph these, we would see that little bump kind of down by like 5, and then you go really, really low as we got further and further out a way, going towards more and more people having this like gene. Because again, there's a chance that 100 people have this rare gene out of the 180, but it's super rare, so that's going to be really, 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 really small probability. But again, it's not impossible. So we got to look at that. All right, so let's try some of these out. So I'm going to go through a series of problems here. I'm going to have you guys try them, and then we will go through them. So here's the first one. Pause, try it out, and then come back. Okay, so if we look at this one here, we expect to need to replace our roof once every 10 years. So what's the probability that in 12 years a homeowner will need to replace their roof twice, right? Well, so my expected time here is one roof replacement every 10 years. So that's going to be 1/10 or 1/10, right? Or 0.1. Okay. So success here is replacing my roof because of damage, right? So again, success isn't always positive things. Just like here, I don't want to replace my roof, but that's what I'm looking for. So I'm going to call that my success state, right? And we're going to want to do a Poisson distribution here because we're looking at, hey, here's the average number of times this should happen in a given time period, right? So to do that, to find my lambda, right, my probability is 0.1, and I have 12 years, or 12 trials in a sense here. My sample size is 12, right, because every year is a sample, effectively. So I would get 0.1 times 12, or 0.12 for my lambda, right? And then to determine the probability of having 2 roof replacements, I would plug in all of those values into my equation, right? So I get E raised to the negative 1.2 times 1.2 raised to the 2 over 2 factorial, and you end up getting 0.2169, saying, hey, there's a little over a 21% chance that I'll have to replace my roof twice in a 12-year period. Okay, second one. So again, go ahead and pause, try this one out, and then come back here and we will go over it. All right, so this one, we are attempting to connect our calls as they come in. After there are 4 unsuccessful attempts, the person gets a message saying, sorry, we cannot connect your call. Please be patient and don't hate us, right? So if there's a 65% chance each time it tries to connect that it works, right, what's the probability that someone gets one of these messages? So success here is us getting through, us connecting the actual call, right? So we're going to want to use a geometric probability here because once we get that first success, we're not going to keep on trying anymore. So like it happens on the first call, we're done. We're not going to attempt a second, third, fourth, fifth time, right? So we're looking for the first time this happens. So that's geometric for us. Okay. So then to find the probability that we get the message, well, we would have to not connect on our first call, second call, third call, or our fourth call here, right? So let's find the probability that we do connect on the first, second, third, or fourth. Because again, that's going to be easier than trying to like find anything past that. Because we're really looking for the probability of it taking 5 or more calls, which goes to infinity. So it's easier to just look at, well, 1, 2, 3, and 4 and take that off of 1, right? So if I plug all of this into my equation from way back here, oops, there we go. My probability of success times my probability of failure times my number of failures. That's what I'm looking for. There we go. So to get that 1, well, that's going to be 0.65 times 1 because there's 0 times that I need a failure, so 0.65. My probability of connecting on 2 is going to be 0.65, that's my success, times 0.35, which is my probability of failure, which I have to have happen once. Then my probability of 3 tries is 0.65, which is my 1 success, and then 0.35 to the second power because I need 2 fails in order to have that happen. Then my P of 4 is 0.65 times 0.35 to the third power because I need to fail 3 times and have that one success. So if I add all of those together and then do 1 minus that total, I get that 0.015. Right? And that is my probability of getting that message because that's going to take longer than for a attempt to connect the call. All right. So the last one that we have here is this one. So again, read through it, then pause it, read through it, and answer those questions, then come back here. All right. So the average murder rate is about 3.6 murders per 100,000 people in the US, right? So in a community of 1,254 people, what is the probability that at least one person will be murdered? So again, this is assuming that the national murder rate is uniform across the entire country. It typically isn't. It changes based off of where you are at, but again, this is for practice sake, right? So what is success? Now this is, again, success doesn't always mean good things, because a success in this case is someone gets murdered, right? My sample size is 1,254. My probability of success is very, very low, which is a good thing, right? 3.6 divided by 100,000 is 0.000036, right? So, is a Poisson distribution appropriate here? Yeah, right? Because when you compute lambda, lambda is 0.045, right? Which is very, very low, and I have a very large sample size. This is an extremely rare case, so this is just what Poisson distributions are made for. They're made for these super rare cases. It's what they're the best at, right? So, to estimate my probability of having 0 murders, right, I plug in R0 into my equation, which is going to be e raised to the negative 0.045 times 0.045 raised to the 0 power over 0 factorial, and you should get 0.956. Right? So that's your probability of having 0 murders in your small town. Okay, well, what if I want to say what's the probability of at least one person being murdered, right? Well, I could do the Poisson for 1 person, for 2 people, for 3 people, for 4 people, all the way up to 1,254 people. But that's going to take a whole lot of time, where I could just find, well, what's the probability of no one being murdered, and do 1 minus that. So, and since I already found that, super easy. 1 minus that 0.956 gives me about 0.044 chance of at least one person being murdered, right? All right, so sorry to end out the notes / chapter on a kind of downer note of people being murdered being a success, but there we go. Here is 5.4. We're doing 1 through 2, and then 3 through 29, just the odds. And that does also conclude Chapter 5. So after this, the next thing we're going to be doing is the review for Chapter 5, which is going to be 3 through 19, just the odds. So with that, I will talk to you guys next time.